Hello everyone, welcome. In this series, I'm gonna talk about engineering differential equations. When I say engineering, I don't mean a proof-heavy abstract math course. This is an application-focused course. We will introduce important definitions and theorems, but the goal is to understand them intuitively, see how they apply to real-world problems, and learn practical techniques to solve equations. So, why study differential equations? Well, whenever you want to describe how something changes with time or space, differential equations appear. Let me give you three examples from physics and engineering. So, the example one is Newton's second law. The simplest one comes straight from classical mechanics, Newton's second law. It says that F equals ma. And since the acceleration is the second derivative of displacement with respect to time, we can write this as d square x dt square. And in time, we can write this as f of t equals m times d square x of t dt square. So this equation tells us how an object moves when we know the forces acting on it. It is the foundation for understanding motion in almost every branch of engineering. And the second example is mass spring damper system. Now let's look at the mechanical vibration example. Imagine we have a mass, and this is a frictionless surface. Imagine we have a mass attached to a spring, the spring constant K, and damper with damping coefficient C. The spring pulls it back with the force of kx of t. So we define our coordinate system as x. And the damper resists motion with the force of c dx dt, if you're familiar with the vibration system. If an external force Ft acts on the mass, Newton's law gives m d square x of t dt square plus c dx of t dt plus k x of t equals f of t. This is an example of second order differential equation. It describes vibrations in mechanical systems, machines, and structures. Solving it helps engineers understand oscillations and design systems for stability. And the third example 3, would be heat equation. This is a partial differential equation. Partial differential equation, or PDE. So finally, for systems that vary both in time and space, we use partial differential equations. For example, the heat equation describes how temperatures U x of t spreads along a rod. So we have a rod, how temperature spread along a rod. And the equation is the partial derivative of U with respect to t is equal to alpha x squared, and alpha is the thermal diffusivity. And solving this equation allows engineers to predict temperature distributions in materials, electronics, and many thermal systems. In this course, we'll cover many topics like first order differential equations, second order differential equations, and systems of differential equations, Laplace transform, and convolution integral, also nonlinear differential equations, Fourier series, and a short introduction to PDE, and many more topics. So that's a plan for the series. I hope you enjoy learning differential equations and see how useful they are in engineering and science. Thanks for watching.